Alright, in this lecture we want to talk about optimization, which is the tool used to actually train the neural network. Before going into optimization, I just want to review one building block that is used in several optimization algorithms. And this is the idea of an exponentially moving average. It's a concept that has been referred to multiple times in the class, but in case you forgot, I would like to review it in a bit more detail. Terms used are exponentially moving average, or maybe even more descriptive, exponentially weighted moving average. In our example that we will see shortly, we'll have a time series of temperature. So this is a figure of this motivating example. We have a time series of temperatures, and the original temperatures are shown in black. As we can see, this black curve is quite jagged, and it jumps up and down quite a lot. So it's definitely not a smooth function. On the x-axis we have the days in a year, and on the y-axis up here we have the temperature in Celsius. And a traditional task that we all know well is to maybe smooth the curve by computing the average of the last k values. For that, it's already important to make a distinction between smoothing at a particular point by looking into the future and into the past. So for example, if you were given this complete time series all at once, then what you can do is, if you are at a particular point, let's say here, you can consider values here in the future as well as values in the past for computing your average or mean. Now, in deep learning, we are typically concerned with computing the averages of, or computing some form of aggregation of the current value and several past values. So if we are at a particular point, let's say here, for our data aggregation, we're only allowed to look into the past. This makes sense, for example, if we are wanting to plot the loss function. The loss function might also be crazy oscillating, maybe even much more so than this black curve that we show here. And in order to visualize it so you can see something, you might want to compute the average of the loss function over the last 10 mini batches maybe. It's not possible for you to look into the future and take loss functions values or loss function values from the future. Similarly, in optimization, we will be concerned about maybe averaging or aggregating some information related to the gradient. Again, we can only look into the past. What were the gradients in past iterations? We cannot look into the future. So what we start out here as a baseline, we are looking at any particular value, and then we try to compute for each particular value, we try to compute the average of this value and the 9 previous values. And this then results in this orange curve going here. So this orange curve is a bit smooth. I mean, it still looks quite jagged, but it kind of removes several of the spikes of the black curve. But what's the problem with such a seemingly trivial thing? The problem is that computing the average over the last 10 values requires us to store an additional 10 values. We cannot simply store one additional value. We need to store all 10. So why do we care about 10 values? Well, we have to consider that we want to compute something like the average or some something similar of the network weights. So there could be 50 million weights or 100 million weights or more. So then a factor 10 makes a significant difference if you need to store 100 million values or a billion values. I mean, that is the difference between very difficult and completely infeasible, considering the memory consumption. Of course, there are architectures that can do that, but if you train on a GPU, this is just not something you can consider. The exponentially moving average, which is shown in red, solves this problem, and it only requires one additional value to be stored. Now that's still a lot, because if we have 100 million parameters in the network and we want to compute some average of the last network parameters, we do need this additional 100 million values to be stored. So let's look at how to compute this exponentially moving average. It's initialized with 0, and so v subscript 0 is the exponentially moving average at time indicated by the subscript. So at time 0 it's 0, and then we have this recursive equation that says that to get the exponentially moving average at time k, it's beta, which is a parameter that we can use to configure this exponentially moving average. We'll discuss it shortly. So beta times whatever the exponentially moving average was at the last time step, plus 1 minus beta times the new information that comes in. So in our particular example of temperature, this would be the new temperature value at time k. So a parameter that makes sense here would be beta equals 0.9. Let's just see how that plays out in a practical example to be very, very simple. So we start initializing the exponentially moving average with 0, and then at time 1, we would take 0.9 times whatever it was before, which is 0, plus 0.1 times the first temperature value. Then we take v2 equals 0.9 times whatever we computed here, plus 0.1 times x2. So we discussed that. As a rule of thumb, the exponentially moving average with beta is similar to averaging over the last 1 divided by 1 minus beta. Let's just check with beta equals 0.9. This would be 1 minus 0.9 is 0.1, so it would be similar to the averaging over the last 10 values. Going back to this figure, now it makes sense that we have this exponentially moving average with beta equals 0.9, and we compare to the orange values, which are the regular averages over the last 10 values. So exponentially moving average looks kind of similar, but since also this temperature time series is kind of extreme, there are considerable differences as well. Let's look at multiple exponentially moving averages in this figure. So black again is the original time series, and then the red line is what we saw before. What we saw before is beta equals 0.9, where we say it's approximately the same as averaging over the past 10 values. Now, setting beta to a much higher value, which means we want to take in something that's more closely to taking the average of the last 50 values or so, then the function is, the output function, the green line, is considerably smoother. It just smoothes away all the spikes going upwards and going downwards. Now going in the other direction, beta equals 0.5, where it's more like averaging over 2 values, we can see that much of the original spikiness and oscillation in the original curve is preserved in this blue line. Another way to analyze this is to start from the end, or let's say some arbitrary current time, which is time k equals 100, and now we want to compute the exponentially moving average at this time step. So we take, and I guess this is kind of switched to make the recursion more convenient. So we write 0.1 times the new temperature value plus 0.9 times the exponentially moving average at the previous time step. And then at V99, the same thing is 0.1 times the new temperature value at time 99 plus 0.9 times the old exponentially moving average. So we can then try to basically unroll this recursion by replacing things. So we would say that, okay, V100 is 0.1 times x100 plus 0.9 times V99. So what is this? We can replace this V99 with this equation above. So we do that. So V99 is now replaced by this 0.9 times V98 plus 0.1 times x99. Okay, that's kind of switched here. And then you just, it's correct, it's just like the order has changed, and then you can multiply it out. And what you get is that doing this a few more times, you see the pattern is pretty simple. It's always 0.1 times the value, then plus 0.1 times 0.9 times the next, plus 0.1 times 0.9 squared times the next, and so on and so forth. So this value here, 0.9, this will be raised to more and more power. So this is just a plot of how the weights of the individual temperatures would look like. So the most recent or current one would be weighted by 0.1. The one in the previous time step would have this weight, and so on and so forth. And you can see that this forms an exponential function. Also, the weights cannot never really drop off to 0. So all the values in the time series, they will all contribute to the exponentially weighted average somehow. So one problem is that in the beginning the sum of the weights is too low, and a proper moving average should have weights that sum to 1. So for example, let's just play this through again. We have start at 0, and then we have 0.9 times 0, which was this value here, plus 0.1 times x1. And what we see here is the sum of weights that are weighing actual temperatures is just this 0.1, sorry. So the sum of the weights is really 0.1, so we estimate, or our weights are way too small. And then in the next time step, we have 0.1 times x1 plus this. So here then the sum of weights is 0.19. So this is gonna basically take care of itself after a while. And then the sum of the weights are going to be very close to 1. So let's look at the figure again. Maybe this figure here. We see there's a problem right in the beginning where the sum of weights kind of needs to catch up to get close to 1. And then it basically doesn't seem to be a problem anymore. Let's just say, for example, we would like to have at the end some average of, we don't want to use the weights, which is a common techniques, but we want to use the exponentially moving average of the weights, the network weights, in the last few time steps during training. In this case, in this application, we wouldn't actually care at all about this problem that in the beginning what we store isn't actually valuable. We would say that, okay, maybe we have thousands of iterations, and after thousands of iterations, this is not such a big deal. We could actually ignore it. In optimization itself, this is a much bigger problem, because when we start out optimizing, turns out that getting the initial weights wrong can cause damage to the optimization algorithm. With the application of high school mathematics, we can figure out this correction term that is equal to 1 divided by 1 minus beta to the power of k, where beta is the parameter of the exponentially moving average, 0.9 in our main example, and k is the iteration number or the timestamp. So again, we want to be super basic. If k equals 2, with beta being 0.9, then we get this correction factor of 5.26. So that is a considerable number, so that will make a considerable difference. Once k equals 100, then we have a correction term that is very close to 1. If in this example k would be 1000, then you already get very close, or get basically below floating point precision. Then it's numerically 1. Now, if we look at this equation again, it's also important to note that the correction factor has to be strictly greater than 1. Here we're comparing the original line that we had in red without the bias correction factor, and the orange line that is the exponentially moving average with the same parameter beta, but with the bias correction. And we can see that in the beginning there's a big difference, then maybe here there's a slight difference, and once you don't see the red curve anymore at all, the orange line is almost perfectly drawn over the red line, which means that when you don't see this difference, then the bias correction doesn't really make a distinction anymore.